This lesson is about gas pressure and temperature. And it's actually going to bring together lots of stuff that you've already learnt about. So what I'm going to do is every time there's something that we've already covered, I'm going to try and do it in this green coloured pen. So hopefully we should be able to see how we're bringing together lots of stuff that you already know from this topic, or that you might already remember from year 7 or year 8, so that we can look at what we know about gas pressure and temperature. So let's start off by recapping what we know about gases. So we know that particles are free to move, and this means that they have no fixed shape. So gases have no fixed shape. We know that they move at high speeds. We know that they spread out to fill a container. And what this means is that they have no fixed volume. Okay, so they'll fill the volume of the container rather than like a solid has that volume. Even if we put it in a container of a bigger volume, it's not going to spread out, it's going to retain its volume. They have a lower density than solids and liquids, which, if we remember that density is mass over volume, what this means is they have less mass for their volume. So they're very light for the space that they take up. And that particles have much more internal energy than solids or liquids. So if we remember from the lesson on internal energy, where we had that graph where as we were heating something, as the time went on, the graph went up and it changed state, and then it went up again. So that internal energy is increasing. So if we look at a gas that was at the top part of the graph, that's got more internal energy than when it's a solid or a liquid. So that's what we already know about gases. Okay, so because gases can move at high speeds, this means that sometimes they collide. Okay, so what do we mean by collide? We just mean bash into something. Or we could think about it as them rebounding off something, because they'll bash into something and then they'll go back in the other direction. And what do they collide with? They sometimes collide with each other. And they also collide with the surface of the container. So the container walls is sometimes how we have that described. Okay, so if you thought about this being like if you were running around in a classroom blindfolded, then you would bash into other people, and you would also bash into the walls, the tables, things like that. So if you think about that, every time you hit something else, every time you collide with a person, or every time you collide with a wall, so like these particles are colliding with each other and colliding with the surfaces of the container, each collision exerts a force. Okay, so this word exerts just means applies. And you might think, well, why do you use the word exerts then? But this word will come up when you do about forces in year 10. This word exert in terms of forces does come up quite a lot. So I'm just introducing it now so that hopefully you might remember when you're in year 10. So if we know it exerts a force, and that's happening over the surface of a container, we should know from year 8 that pressure is equal to force over area. Okay, so this was an equation that you did probably at the end of year 8. So if there's a force that's being applied over an area, so the surface of the container, then that is what is going to be pressure. Okay, so if we to increase the pressure, we either need to increase the force or decrease the area. So it's going to be thinking about this force that is going to kind of tell us about gas pressure. So let's think about changing the temperature. So to recap, we know from the internal energy lesson that if we increase the temperature, then we will increase the kinetic energy of the particles. Okay, so if we increase the temperature, the kinetic energy of the particles increases. We've already done about that this topic. Okay, we should already know from P1 that the equation for kinetic energy is equal to 1/2 times mass times speed squared. Okay, so if we've increased the temperature, we've increased the kinetic energy. If we've increased the kinetic energy, we've increased the speed. Okay, so as kinetic energy increases, so does the speed. Hopefully that all makes sense. Okay, so now we need to think, if you've got these particles that are moving around, they're colliding with each other, they're colliding with the surface of the container, and their speed increases, how is that going to affect these collisions? Well, what it means is that particles collide more often and with more force. So each force is increased, and there are more of these little forces that are being exerted. So let's summarize this. When temperature increases, pressure increases, because there are more collisions with more force. Okay, so that's a summary of all of this. Okay, so just to recap, pressure is force over area. The forces come from the collisions of the moving particles with the surface of the container. If we increase the temperature, the particles have more kinetic energy. An increase in kinetic energy is an increase in speed because of our equation that we already know. So if they're moving faster, they're going to have more collisions, and each collision is going to have more force. So what that will mean is an increase in temperature increases the pressure. So that relationship is something that you need to remember. So you might be thinking, how do we know that this is how gases move? And there's one more thing that you really need to know about. So we can't see air moving or gas, but we can see the effects. And this is called Brownian motion. So this is Brownian motion, is how we know that these particles moving randomly in random directions. And it was a scientist called Robert Brown who first observed this. He wasn't the first to be able to explain what it meant, but he was the first to observe it, which is why it's called Brownian motion. And we can actually see this by using something called a smoke cell. Okay, and this is basically a chamber that you just kind of set a piece of paper or something on fire so it produces some smoke, so then blowing it out. So you're going to trap some smoke in a little chamber. Above the chamber is a microscope that you can look through, and all that needs to happen is some light needs to pass through the smoke cell. So the reason for this is a smoke cell. Smoke is bigger particles than air. So we can't see air with a microscope, but we can see smoke particles with a microscope. Okay, so you can see with a microscope. So what happens is, if we imagine we're looking down this microscope, so we're going to see, because you've all used microscopes in year 7 to look at like plant cells and stuff, so there'll be a circle. So let's imagine that we've got our smoke particle. It's quite a big particle here, okay, and these will be our air particles, but we wouldn't be able to see them, but I'm just drawing them so that we can see what they would be like. So we would have our air particles that would be travelling in random directions, and as we know, they're going to collide with the walls of the container, they're going to collide with each other, and they're also going to collide with our smoke particle. And when they collide with our smoke particle, they're going to move it. So if the air wasn't moving, then our smoke particle would be stationary. But because our smoke particle is moving, what that tells us is the air that we can't see must be the thing that is exerting this force to move it around. We're going to have a go at some questions. So as usual, have a look at the question when I first read it. Pause the video, have a go at answering the question, and then play it again so that you can look at me going through the answer. So in the following text, highlight in one colour any descriptions of particle behaviour, and highlight in another colour any properties of the state of matter. So we need 2 highlighters. The first thing that I'm going to do is decide what colour, so descriptions of particle behaviour. I'm going to do in this light green colour. Okay, so let's do these one at a time. Descriptions of particle behaviour, so read through and highlight the bits that are describing how particles behave, and then get your other colour and then read through and then highlight any properties of the states of matter. So solids. Particles in solids are held very closely by interatomic forces. That's a description of their behaviour. This causes solids to be very strong and difficult to separate. Solids hold their own shape. Particles in a solid do not move around very much. That's behaviour. And simply vibrate in their spot. Liquids. Particles in liquids are very close to each other and are in contact, but they can move past each other quite easily. That causes liquids to be very easy to separate, and this is why they do not hold their own shape, but take the shape of the container they are in. Particles in liquids move around all the time and bump gently into and past each other. Gases. Gases have particles that move around very quickly and that are very spread out, so there is lots of space in between them. That means that you can compress, squeeze gases very easily. Gases not only take the shape of their container, but they fill the whole space of the container they are stored in. So that's the behaviour of the particles. That's what the particles are doing. So now we need to go through and highlight in another colour properties of the states of matter. So we're not going to be highlighting any of the things we've already highlighted, and hopefully this will make it a bit easier for us to spot what we need to be highlighting. So have a read through. So I'm going to read all of it. Solids. Particles in solids are held very closely by interatomic forces. That causes solids to be very strong and difficult to separate. Solids hold their own shape. Particles in a solid do not move around very much and simply vibrate in their spot. Liquids. Particles in liquids are very close to each other and are in contact, but they can move past each other quite easily. That causes liquids to be very easy to separate, and this is why they do not hold their own shape, but take the shape of the container that they are in. Gases. Gases have particles that move around very quickly and that are very spread out, so there is lots of space between them. This means that you can compress gases very easily. Gases not only take the shape of the container, but they fill the whole space. Apologies, that's a property, it's not particle behaviour. I do apologise. Now, with the help of the diagram, put the following phrases into full sentences to describe how the particle model can explain how a gas exerts pressure on the wall. So we've got this diagram here, and we've got these key phrases: move randomly, exerts a force, collide, container walls, average force per unit area. So have a go at this. Okay, so remembering from earlier on, each particle moves randomly in the container. Okay, so we've done that one. So, when a particle collides with a container wall, it exerts a force. Wow, one sentence, three things. So we can see this on this diagram here, where there's a collision that's happening here. So there's a force that would be exerted at that point. Okay. So the pressure is the average force per unit area. So the average force just means that there are lots of forces that happen. Particles travel at different speeds to each other and in different directions. So it's just taking an average of all of those. They're not all travelling in the same direction. They're not all travelling at the same speed. So therefore, we use the phrase average force. Question 1. Describe the general behaviour of particles in a gas. Okay, so we've already looked at this already, but let's recap again. So particles are far apart. Okay, that's one important thing. It's 2 marks though, so we're going to need to say something else. And they move freely at high speeds. We could say rapidly, that would be okay. Good. Describe how this behaviour changes as temperature increases with the gas in a container with a fixed volume. So what happens when temperature increases? That particles move more quickly. Or we could say that they have a higher kinetic energy. state the definition of pressure. When it's asking for a definition of something that you have an equation for, you can just give the equation most of the time. So we could say force per unit area is the proper definition, but usually at GCSE you could write pressure equals force over area, and you would get a mark for that. Okay, so now let's think about a scenario, because we would do this if we were in school. We would do this practical where there would be a sealed glass bottle that we would put in a bowl, so it would be connected to a pressure gauge. So it would look like this. Let's just sketch it. It's like a round bottomed flask, and this is connected to a pressure gauge, so it has like a dial on it where that will change where the pressure, if it increases it goes that way, if it decreases it goes that way. And then we normally put it inside a bucket that has water. So we have gas inside of here, and then we change the temperature of the water that's in here. And hopefully we should know from P2 when we did about energy transfer by heating, if I put hot water or increasing the temperature of the water that's here, then that is going to increase the temperature of the gas that's inside here. And then we would look at the temperature change that would be on the pressure like meter at the top. Okay, so the pressure gauge, sorry. So that's what this is called, a pressure gauge. Okay, we'll show you this in September, don't worry about it. So a sealed glass bottle of cold air is placed into a large bowl of hot water. Complete the table by ticking one correct box in each row. So the mass of the gas, is it going to increase, stay the same, or decrease? Well, it's a sealed bottle. We're not putting any more gas into it, so the mass will stay the same. The density of the gas, is it going to increase, stay the same, or decrease? Well, if we remember that density from the first lesson is mass over volume, so it's mass divided by volume, we've just said the mass will stay the same. And if it's a glass container, the volume can't change either. So if the mass is the same and the volume is the same, the density has to stay the same. The speed of the molecules in the gas increases, stays the same, or decreases. So the scenario is that we've got cold air being put into hot water, so the temperature is going to increase. If the temperature increases, the speed of the molecules increases. The pressure exerted by the gas increases, stays the same, or decreases. If the speed of the molecules increases, there will be more collisions, and those collisions will have more force. Because pressure is equal to force over area, therefore the pressure will increase. And the volume of the gas increases, stays the same, or decreases. Again, if it's a fixed glass flask, then the volume is not going to be able to change, so the volume will stay the same. Okay, so this is the Brownian motion part, and let's just read through this bit together and then try and fill in the blanks and then label the diagram. So Brownian motion was observed by the Scottish botanist Robert Brown in 1827. During his research, Brown noticed that pollen floating on water showed very rapid, irregular and zigzag movement when looked at through his microscope. He thought that this motion was due to some unknown vital force that all living matter must have. As Brown had limited equipment and techniques, he could only demonstrate that this motion was not caused by convection in the liquid, currents or evaporation, but he couldn't give an explanation for the motion he observed. Einstein and the Polish scientist Smoluchowski each gave an independent explanation of the observations in 1905. So this is just a bit of background to the Brownian motion that we looked at earlier. So Albert Einstein and Marian Smoluchowski understood that the random movements of the large particles suspended in a fluid were caused by collisions with the molecules in the fluid. The molecules of the fluid are too small to be seen directly, but the particles in suspension are very large compared with the molecules of the fluid, so they can be observed with a microscope. Label the diagram in the box below of an experimental arrangement that can be used to demonstrate Brownian motion. So let's start. Number 1 was this bit here, which we called a smoke cell. So it's just a little box with some smoke inside it. Number 2, light shining through the smoke cell. Number 3, a microscope. And number 4 is the view through the microscope. And this line shows us the random, so it's the path of a smoke particle moving randomly. And then a summary. The pressure of a gas is caused by the random impacts of gas molecules on surfaces. If the temperature of a gas in a sealed container increases, the pressure of the gas increases because the molecules move faster, so they hit surfaces with more force. The number of impacts with the container walls per second increases, so the total force increases. Brownian motion describes the unpredictable motion of particles in fluids due to collisions with particles in the surrounding medium.